Alright, hey guys, what's going on? So today we're going to be talking about counting particles within our scalar complex valued fields, or complex valued scalar fields, however you want to say it. And we are going to now be we're going to be understanding these fields more in an intuitive way. We're going to be looking at how we can use number operators to count the number of particles within these fields as well. And so let's go ahead and get started. Make sure to hit that like and subscribe button, and make sure to go onto my Patreon page if you want to support there. If you want to support here on YouTube, you can also become a member here on YouTube. I'm getting the progress of this YouTube channel is going great. I'm really loving the direction this is going, and we're going to be doing animations and all this later. So, okay, with that being said, let's go ahead and get started. So, in this video, we want to dive a little bit deeper into the raising and lowering operators. Initially, we found that these operators, when applied to the Hamiltonian, they raised it and lowered the energy of our free scalar quantum fields, complex valued quantum fields. And these operators take on a new meaning when we apply them to the number operator. Okay, so let's take a look at what a dagger does, and then you'll be able to see what the logic is, and you'll be able to do these derivations for not just the A dagger operator, but the A operator and the B dagger and the B operator. And these calculations are going to be very similar. So we're just going to do one, and then for practice you can do the others, or you can just take my word and I'll provide the results. But we want to understand what happens when we use the A dagger operator on nk. This is just some arbitrary state where nk is the number of particles of momentum k. Okay, we want to know what the result is, and we're going to call that result mk. We don't know what this is yet. We want to calculate this in terms of these guys. Okay, so let's go ahead and do that. Here we don't know what mk is, which is what we're striving to understand. And so to do this, we now want to apply the number operator. What we're going to say here is that the number operator operating on mk, this state that we don't know what it is yet, is this right here. So we're just literally replacing mk with this right here. So we put it right here. And then what we do is we say, well, I'm going to underline this bit that's right here. We define this thing. I'll do a different color. We define this thing in the last video as being this guy right here, okay? And then with our commutation relationships, we said that a dagger that was equal to Kronecker delta k. This pen is very picky. Minus k prime, and when these are operating with just k, then this is just going to be that's going to be 0, and that's going to be 1. There's going to be some normalization factors in here, but we're going to take that 1 to we're just going to take it to be 1 right now, and then what we get is, because the normalization factors, what happens with the normalization factors is that we're integrating over some volume, right? What is it? 2 pi. We have d3k to omega. We integrate over some volume, but then this guy here, right? This guy here, well, that has our 2 pi cubed 2 pi cubed to omega as multiplied by this. So this guy multiplied by this, but it's in the denominator here. So effectively, those things are going to cancel when we do the integration. So we're ignoring that. We're just saying we are looking at the Kronecker delta and what that does at momentum k. All right, and so that's where we get this 1 from, right? So this is a dagger, a dagger, and that is going to be, if I do a different color, this bit right here and this bit right here. This is the commutation relationship, right? So then from here to here, then, well, this is just a number operator. Okay, so we put the number operator back in, so we have this thing, and then we split this up, right? So this times this, and then this guy times this, right? So we have this, and then this here, well, that's going to stay the same. This here, well, that is going to be nk, right? So the eigenvalue for NAK is going to be the number operator. This is the number of particles at momentum k of type A. Okay, again, type A, that refers to the field. Remember, we have two fields. In most of my videos, I've called the complex conjugate with a bar over, but sometimes you'll see it like this as well. But we have two fields, right? Two fields, or really one field, but we have this one and this one. This is the complex conjugate of the field. So complex conjugate field, and this is the field itself. So field field. And of type A, well, that is for this field right here. So type A is this field right here. And then type B is going to be for this one. Okay. Fundamentally, what we found out was that these are related by opposite charges. So, okay. So the number of particles at momentum k, that is the eigenvalue for this operator. Right, so then we get this here. So just to, so to get from here to here, we're just factoring out a dagger, right? And we get this A plus 1, or NK plus 1. All right. And, right, because this is going to be A dagger times 1, which gives us this, and then N A dagger, N A dagger. Okay. So then from here to here, then, well, this here, this right here is this up here. Okay. And so what we're doing now is we're saying we're replacing that with MK, right? We're replacing that with MK. I'll do that same color. And when we replace that with MK, then we get this relationship. And then we can see here that NK, or NK plus 1 times NK is equal to this guy right here, because we said that this here is our MK eigenvalue, right? So this thing, right? So NAK operating on MK, this is the thing we didn't know, is equal to this right here. Okay, and so we're saying that the eigenvalue for this thing, acting on some arbitrary state, well, its eigenvalue is this, NK plus 1, right? So that's the number operator acting on MK has an eigenvalue of NK plus 1. This is a state with NK plus 1 particles having 3 momentum, and so hence the A dagger acting on a state increases the number of particles of K 3 momentum by 1. This creates a particle, okay? Because it's increasing it by 1 quantum. Okay, this is not 1/2, not 3/4, by just 1. So we can do a very similar calculation to show the effect of all the other creation and annihilation operators. So we can do the same exact thing, the same exact procedure, and what we get is all of this, right? So, and what we're going to do is we can contrast all of these with all of these. We established these already, right? These are the creation and annihilation operators in the context of H. Here we have the creation and annihilation operators in the context of N. Again, so NA operating on this is going to give us N minus 1A times this, and this is going to give us plus 1, this is going to give us minus 1, this is going to give us plus 1. And so, and these are of the different type field, that conjugate field. That's why we put the bar over there. And so in English, this means AK destroys a particle with momentum K. A dagger creates a particle with momentum K. These guys, again, are associated with that field, and then these guys are going to be associated with that field. Similarly, these guys are going to be associated with, nope, not that field. That field, and these guys are going to be associated with the complex conjugate of the field. And these guys here, we're raising and lowering energy, not raising and lowering number operators. And so we can see that from the creation and annihilation operators that there's a tight relationship between particles and energies for our field. All right, let's continue. This video might be a little bit shorter than others, but that's okay. So our creation and annihilation operators only make sense then in context, right? Because they need to be in the context of some other operator out here, some other operator, and then they'll be able to create and destroy particles or energy. And this is going to come down to, when we start talking about propagators and generators, this is going to come down to particles being destroyed and created in what we're going to call a black box, and the black box being the thing where our Feynman diagrams are happening. And we'll get into that, but right now we're sort of still just laying the groundwork here. So what about out of context? So we've calculated these for within the context of number of particles. We calculated them in the context for energy. The next question is, well, what do they do out of context? Well, let's go ahead and calculate that. So to answer this question, we seek to find the number A prime in this equation here, right? So we want to know what happens. So if we're operating AK on N, well, that's going to take us to one less energy state, or one less particle state. And is there some normalization factor out front that this is going to be, that we're going to need to put out here? So we could take the complex conjugate of this to get this. So this process here is we want to find A prime. Okay. So first things first, we're gonna take the complex conjugate. When we take the complex conjugate, well, the complex conjugate of our ket vector is our bra vector, and we take complex conjugate of our A, which is A dagger. All right, and then this guy here, well, A dagger. That is going to, the effect here is that it's going to raise particles in the ket state, but it's going to lower particles in the bra state due to complex conjugation. And then we can so putting this on hold, then we can calculate this, right? Because this here, this bit right here is this right here, okay? And then so we replace this then. We replace this then with this. All right, and this thing with this, right? Because we've calculated that right here is right here, which is right here. All right, and then we take our constants out, right? And we get this with this. That's just one. This is like an inner product between states, and then we get this parallel to all this. We can do this also. This is the number operator. Which is equal to this, as we've seen before. Okay, this thing is equal. Its eigenvalue is nk. All right, and so we could take that number out, that eigenvalue out. This is just one, again, inner product between states of the same or two similar states, and so we get nk. And so what we get is that A prime dagger times A prime has to equal nk. Okay, and so therefore we have this, right? Because A prime then has to be the square root of that. okay? Because it's squared, it has to be this. And so that means that we have this, right? So this coefficient is now placed in here. We can do the same thing for our creation operator. So same procedure, right? You could pause the video, I'll go through this a little bit fast here, but same procedure. We take complex conjugate, rewrite, and then rewrite again, and then do the same thing here, right? A prime, we're really just doing the exact same thing in this procedure. This should be a dagger. Sometimes my computer doesn't work when I'm doing this, but that should be a dagger. And then we have this guy here, and then because the A prime, A dagger, we're using the, here we do the complex not the complex conjugate. This is commutation relationship, as we've said up here, as we were talking about up here. Right, so that's commutation relationship. And then, so our eigenvalue then is this guy, and so this times this has to equal this. Notice there's no primes here, so the prime is for A, and then no prime is going to be for A dagger. It doesn't really matter what you just have to keep track of what your nomenclature is, whatever you're doing. So we have this and this. So in the end then, so this squared equals the square, so one of these has to equal the square root of that. So we get this guy, and we can do the same thing for B dagger and B. And what we end up getting ultimately are all of these relationships. So out of context, these things have normalization factors in front of them, which look like these. Again, we have for the prime field, or for the complex conjugated field, and then for the not complex conjugated field. All right, so let's sum everything up and call it there. So here we have it, everything we need to know about our complex valued scalar coefficients. We have these normalization factors. We have a number of particles. So A dagger, B dagger, B. These are all within the context of our number operators, and then all within the context of our energy or our Hamiltonian operators as well. Again, this is all in a free field. We haven't talked about interacting fields yet, and we're going to get to that. But this is what we have so far. We have normalization, number of particles, total energy. These things are raising and lowering all of these, and they have normalization factors in front of them as well. These things here, they're not eigenvalue equations, right? Because this state is not the same as this state. But to get from nk to n plus 1, or nk plus 1, we need this square root factor out in front. So going forward, what's nice is that for spinor fields and gauge fields, they're going to have very similar dynamics to them. Obviously going to be more complex because we're adding more we're adding more degrees of freedom, spin, and so forth. But everything here is going to be very, very eerily the same, or very similar to this. So next thing on the agenda is going to be spinors. We're going to talk a bit about spinors. We might take a few videos to talk about them, but that's going to be the next thing we want to understand. So we've talked about scalar fields, and scalar fields, again, those are just numbers, right? So numbers, so scalars, those are just numbers. Spinors, then, this was the Klein-Gordon. Here we're going to have the Dirac equation. And then when we talk about vectors, this is going to be the Proca equation, or Proca-Lagrangian. And then we're probably not going to talk about tensor fields. But tensors, that's GR, general relativity. There's these weird things called twistors. This is probably going to be a whole new playlist, but I want to talk about these things because I've read up on them quite a bit. They're quite interesting objects. They require us to understand something about complex projective spaces, though. We haven't talked about that. So these objects here, there is such thing as twistor fields. This was developed by Roger Penrose back in the 1960s. But this is probably going to be a separate playlist, which I'm probably going to start soon because I've started working on slides for these. But this can be a separate playlist. Separate playlist. All right. With that being said, I hope you guys like this type of content. Make sure to hit that like and subscribe button. Again, you can become a member here on YouTube to support the channel, or you can also become a member on Patreon and support over there. With that being said, I will see you guys in the next video.